So this is the Computational Sustainability Online Graduate Seminar, in short COGS. The seminar has the purpose of disseminating research in the computational sustainability network among postdocs, graduate students, and it can be work in progress or finished work. And today we're going to have Roel Dobbe. Is that correct? Dobbe?
Roel Dobbe.
Again?
Roel Dobbe.
Roel Dobbe. Okay.
Yeah.
Talk about an integrative approach to data-driven monitoring and control in electric distribution networks.
Thank you. Thank you for having me, and it's exciting to share my work. This is my my PhD work, which I finished last spring in 2018 at UC Berkeley in the Department of Electrical Engineering and Computer Sciences. Over there, I worked with Professor Claire Tomlin and Professor Duncan Callaway, and a broader, I think, really exciting community of researchers in energy, power systems, but also other engineering disciplines, including connections with the Lawrence Berkeley Labs up on the Hill in Berkeley, one of the national Department of Energy labs. And so in this talk, I'll be giving an overview, going into a few projects, a few chapters of my thesis. There's more material than I can cover. So if there are any things I've announced in the abstract that I'm not getting to, feel free to reach out to me, and I'm happy to share materials and discuss afterwards. As I mentioned earlier, I'm now a postdoc at AI Now. The AI Now Institute in New York University studies the societal implications of artificial intelligence, and I'm one of the technically trained people there, one of the few, and part of what I'm doing is trying to look at how do we integrate machine learning based data-driven technologies in safety critical environments. And so my work is also shifting a little bit to not just looking at energy, but also looking at other domains, including policy discussions about criminal risk assessments and other policy domains. So if there are people on the call who would like to talk about that, I'm also very much open to connect afterwards. So let's dive in. What I start off with is this question of, do we have a revolution in automation? And I think this I've used this slide for a few years. Most people now are familiar with this idea that automation is showing up everywhere around us. And the way that I like to frame it is that really we have a lot of different ingredients for automation that have been or that are being commodified. So we're seeing data, access to data sources everywhere. There's more and more algorithms and computing that's readily available that we can connect or that we can repurpose. We see more and more devices and sensors that are there to help us know or actuate a system's state. And of course, with that also connectivity. And so these, I think, thinking about these as like commodity ingredients is one way of trying to be creative about what is possible. But it also allows us to think a little bit more about the broader infrastructure or the broader ecosystem in which we are engaging and in which we are, playing a role, whether it's as a computer scientist building algorithms or a data scientist trying to make sense of large data sets. So that as a context. So for me, I've always been what's the right word? I've always been impressed or been interested in this rise of automation and how it changes our own lives. But I've particularly been interested in how it affects existing legacy infrastructures. So think about electricity nets, grids that we're talking about today, but also transportation. Thinking about medical environments in which there's a rapid introduction of data-driven analyses, but also more and more data-driven treatment plans. And yeah, there are a lot of questions that come with it that are not just technical. But the main question I have tried to ask is, how do we integrate data-driven decision making in these critical infrastructures and services, while ensuring that we do that respecting various values, so values of safety, but also values of privacy, and increasingly I've been also looking at the debates around fairness and what that really means in the context that I'm working in. But I think with that also, I've been interested in kind of a zeroth order question, like what are even meaningful forms of data-driven decision making? As we see that there's so much happening, and we're all trying to, trying to contribute. And for me, first of all, what this means is really trying to understand the context in which you're working. I've been working before or in between my master's and PhD. I am from the Netherlands, and I worked in the Netherlands as a consultant, and I worked a lot with utility companies. And so it gave me some context and some sense of not just what might be possible with data-driven technology, but also what are the institutional challenges, and what are the legacy systems, but also the ways in which operators operate systems. And so having that sensitivity is also really important once we start to do more sophisticated control and decision making that is oftentimes miles away from the context or from the existing systems. And so being able to interact with utility professionals and policymakers is, I think, really important as a zeroth order question to inform your technical design and your technical work. And I think it can really make a huge difference in coming up with ideas that can then be implemented and land softly or land smoothly in in a policy space or in an actual application domain. So what I've done during my PhD is I've worked in the medical space, in systems biology, working with cancer biologists on data-driven diagnosis, and a little bit on automated treatments, or thinking about like how would you schedule treatments in order to move, in this case, breast cancer, so a tumor or tumor cells into different states where they're easier then to treat or get rid of. That's not the focus of today's talk, but just give you a sense of other areas I've worked in. Today I'll be talking mostly about my work in electric grids, a little bit about state estimation, and then most of the talk will be about data-driven, decentralized, optimal power flow. I will not go into the differential privacy work, but I'm happy to talk about that offline. So the context for that, we're moving from what I would call a fairly calm way or a fairly calm power distribution grid, where we used to have unidirectional power flow. We used to have monotonic voltage drops and fairly predictable loads. And most of the existing infrastructure would be dimensioned based on peak loads and a safe margin on top of that. And from there, we're moving into a very, very different and highly dynamic setting. And it's happening around us. So a new standard with more renewable generation, electrification of many things, in and around our house. Intermittency comes with that. So the intermittency and variability due to both the distributed generation through solar, but also the more dynamic ways in which we are using electricity. With that comes bidirectional power flow, which has a huge impact on the infrastructure. But we also have more and more sensing and abilities to control through both at the utility level, having more smarter forms of capacitor banks or switches in the network, but also at the end nodes, so through electric vehicles, smart thermostats, etc. And so that with that comes a whole new way of thinking about controlling and operating the network, but also new challenges. So if we just let all this new technology enter the system without thinking about a new control paradigm, what we see is we'll see more and more increased switching and wear. So the existing infrastructure might wear out a lot faster, leading to higher economic costs. With that also comes new safety risks. And what we see now happening is that there are many territories where utilities are putting limits on renewable integration because they haven't been proactive enough to think about what the impact of more and more renewables distributed through the system might be on their existing legacy infrastructure. Also important to note here is that there are emerging values and concerns, so around privacy. So utilities might want to use our smart meter data in order to have a better understanding of this dynamical behavior in the network. But what does that mean for our privacy? Just as an example. So we're moving, what I think, to a new paradigm for operating the grid from a central operator model, which is very reactive. So it used to be that, and it still happens, that operators would have like a big paper map on the wall where they would put pins to indicate the status of switches or potential places for maintenance. And we're moving away from that, or with that as well, reactive in a sense of like if there is an outage somewhere, an operator would literally wait for someone to call and let them know. And we're moving now very quickly to a more an operating paradigm that's a lot more proactive, that is more distributed and decentralized with, like I said, with controllable devices that enable like very localized control, and that also kind of through which we can also invite more participatory control schemes where we are as consumers are and prosumers, so producing energy, are contributing to preventing congestion in the network or minimizing losses in the network, etc. And so the way I'd like to think about this is where we really have to adopt a more control theoretic lens. If we want to start like using all these sensors and actuators in a meaningful way and in a way that we can design safe and reliable new operating schemes. And so here we see kind of a general picture of what a control systems diagram looks like, block diagram looks like. And I will use this moving through the presentation kind of as a way to show where I have been trying to make some contributions to build this, because we are, we're far away from having like a fully deployed like control system that is really kind of sophisticated in a way that we apply this theory to airplanes or other systems that have in which control theory has had an important role throughout history. So just to say here is like, think about these different variables. Like X are the state variables of your system. So this could be like voltages or power production or consumption at certain places. D are the disturbance variables. So these are variables that affect your system and that you don't necessarily, that you cannot necessarily measure. Z are the sensed variables, your measurements, and U are your input. So these are the variables you can change. So these might be switches, or these might be like controllable batteries. And R here on the left side is a reference variable. So let's say you want to control the voltage to stay around its nominal value. That nominal value would be R. All right. I'll first talk a little bit about like system, because with building being able to build feedback and feedforward controllers comes like having the need for having understanding about the system. And what we've done at Berkeley is thinking about linear models that can enable optimization and control. And so we started off with looking at a very common model. It's called the disk flow equations, which have been used and cited heavily since 1989, which they were developed in Berkeley as well. I forgot to include the source here, but the disk flow equations, or sometimes called branch flow equations, if you Google that, you'll find those papers. And so what these do is they basically cast the branch flows on lines as on wires in the network as capital P being, kind of a sum of all the nodal power injections or consumptions, small p. Same for reactive power Q. And underneath you see delta, which is the angle between node M and N, or the angle difference, sorry, and delta V squared is the squared voltage difference between node M and N. And these can be cast as a linear combination of the branch flow between node M and N, which is called here Pn, so P flowing out of N and Q flowing out of N. And X and R here are the resistance and reactance values of line Mn. So without going into detail, on the right side, what we've done is also trying to extend this to 3 phases, because it's really important in distribution networks to take account of the unbalanced nature due to it being 3 phases, and especially the further we go in a network, the more unbalanced we will see. And so we've worked on a 3-phase version of these disk flow equations that have helped us to enable linear mapping. So here we have, again, a linear mapping for Z and X. So Z are our measurements and X are the variables in the system, the dynamical or the system variables. And so these linear mappings here, in short, characterized by matrix ZM for measurements and ZE for what we want to estimate. They map the vector S, which are our nodal power variables, small p, n, and qn, to measurements and states. And these then, as I said, enable application of existing control and optimization ideas and other analyses opportunities. And so with that, I started thinking about state estimation. So I started thinking about, can we use this model to allow getting information out of our measurement Z in order to update or have an estimate of what our variables X are in the system that we might want to base our feedback control on, or some kind of control scheme on. So I'm going to go over this a bit quicker and then spend a bit more time on control later on. But what we did here is building a forecasting-based state estimation for 3-phase distribution systems. So state estimation has been around for a long, long time and is mostly based on, historically based on weighted least squares, in which you would need a lot of sensors in the network in order to have a well-posed estimation scheme. And so since we anticipated that a lot of utilities will not have that many sensors or that many reliable sensors in the foreseeable future, we thought about what can we do if we have a limited set of sensors. Can we blend that information with data from, smart meters or other SCADA data, so supervisory control and data acquisition systems that utility use, and perhaps other kind of data that can forecast the load in a network, such as weather data. And so here on the left, on the top, you see this flow diagram where we take data, we build forecasting models to model the load. We then use this network model that I just showed to produce forecasts of voltages, both the ones that we will try to estimate in real time, X hat, and those that we can actually measure in real time, so Z hat. And so with that as a forecast of what the voltage might be, we're then taking the real-time measurements Z to update our prior. So it's a Bayesian approach. Here you see an example of what it does, or this is actually an example of the load forecast. So we have we use Gaussian process models to get a sense of both a point estimate. So x hat and z hat are the mean of the Gaussian process, and then also the second order statistics, which we needed to build this state estimator. With that, we could think about Bayesian estimation, and in the linear case, that draws down to a linear least square estimator. So that looks a lot like the weighted least squares, but is a closed form solution that is like a linear equation in which all the variables here, except for z, are basically statistics that you know a priori. So you can have those ready and measure z and update your belief or your estimate of x in real time very, very quickly for large networks. And so this just shows you that this closed form solution is actually the result or the minimizer of this least squares problem. So yeah, what I said before, those linear mappings that you see here at the top of the list of equations, they allow us to build these statistics. And so this is how the statistics then look like. This is the result of using this method on an actual network for Alliander, which is a utility company in the Netherlands. And here what we had was a network that had only a few measurements at the bottom, at the top, I think. And but we had some historical smart meter readings from a number of houses throughout the network, not all of them. So we used those readings to build the best forecast that we could. And here you see that in the black dotted, not the dotted, but the dash line, a predicted voltage drop is what we forecasted a priori. And then the estimated voltage drop is in green, and you can see it follows the actual measured voltage drop across the network a lot better. And so what this tool really allows utilities to do is to make as much use of very few measurements, so both like the real-time measurements, in this case only 2 in a network of I think roughly 130 buses. But it also, so both limited real-time sensors and limited, historical data. And of course, this is not as good as having like a full-fledged state estimator. But the thing is, if you're using the historical or the traditional methods, you wouldn't be able to have a well-posed problem. So this Bayesian approach is it might not work in certain conditions. You're doing a projection, so you're throwing away some information, and there are some implications for, based on where you place your measurements for what kind of voltage drops or what kind of voltage differences you might be able to measure. So this is kind of a compromise in a transition towards more scenarios where we have a lot more sensors and can use the traditional methods.
May I ask a question, Roel?
Yes.
So can you explain again what the difference in information between the estimation and the prediction is? So prediction is just without any sensor measurement?
The prediction is purely based on taking historical load data, building a forecast model for those loads, okay, and then mapping that to a voltage differences through a linear mapping.
I see.
So it just uses, say, the predicted voltage drop here just uses historical data, and the estimated voltage drop takes this value for the measurement. So it takes the predicted measured voltage and compares it to the actual measured voltage difference, and then maps it through the linearly squares mapping. So this is the equivalent of what a Kalman filter would do for those of you who are familiar with Kalman filters. So it's basically a one step in a Kalman filter. And so if you would do this like repeatedly, it's not, because this is not a dynamical system, but you would be able to kind of keep tracking the red dotted line here just by as your measurements change, and what you're doing is you're continuously comparing the measured voltage drop to what you predicted that the sensors would tell you.
And you estimate how many data points in advance? Just one, or?
So in this case, you can actually estimate any voltage difference that you're able to, that your model has. So what I'm showing you here is, I think we had 3 measurements here. 2 we used for as measurements in the estimator, and then the 3rd we used to validate. And so we modeled the, let's say you have a measurement at the end of the network, at the start of the network, and somewhere in the middle. What we did was we can predict, based on this load data, we can make predictions for any point in the network.
I see.
So we predicted that as well for the middle point, and then we looked at, then we took the other 2 measurements to update that middle point prediction, and then we compared it to the actual measurement of that middle point. So in this case, we needed to keep one measurement aside to be able to validate, or to be able to validate our system. But you're never sure, but you can also predict and then estimate other points in the network.
Okay, thanks.
All right, so this was a very quick presentation about state estimation. We have actually validated, as I mentioned it, on a what's called a neighborhood battery system. So this Alliander has this pilot that they ran that they're now copying to other places, where a neighborhood, so a group of houses, is sharing a community, what they call a neighborhood or a community battery that has lots of sensing and controls capabilities. So in this case, we were just using the data that this battery or this system is collecting, and this information is not necessary. As I said, it's not as good as a full-fledged state estimator, but it will provide data about the network that can then be used a priori to do more analysis on like what's happening in networks and how they might use that. They could use that information to update networks. Where to place these batteries or other kinds of control equipment, etc. So this was the network that we used, which has, I think it has, I don't remember the number of houses, but the number of nodes in the model was, I think, 137. But it's in the paper that's on archive for those of you interested. So that was state estimation. And now we're moving, I want to talk a bit more about feed-forward control. And this work has since evolved to also think about feedback, but I'll just focus on my work, my thesis work, which was trying to think about feed-forward control based on machine learning. And here we are, let's see, yeah. So here the setting is that we're trying to use inverter capability. So inverters that interface different kinds of devices, storage devices, electric vehicles, solar installations, or smart loads to the network that are a capability to do energy conversion from DC to AC or vice versa, but that also have sensors on them, have localized computation and communication abilities. So the idea here was, can we use these devices to control the system, but also how might these devices use machine learning in order to operate in a decentralized way or in a more independent way, while still, maybe optimizing for some local objectives, but while also satisfying or respecting the network constraints and objectives. Yeah, here we also worked with Alliander and with TU Delft, the student from Delft, where I also used to study myself, and with Berkeley National Labs. So in looking at the literature at the time, there's more now, but we can broadly distinguish between two types of control paradigms. On the one end, we have system-wide optimization-based controls, which is optimal power flow, and there's been some theoretical advances, roughly 7-8 years ago, that allowed for casting a wide set of optimal power flow problems that are typically non-convex as convex problems. And based on that, there's been lots of work that uses optimal power flow to do dual decomposition, semi-distributed implementations. And overall, what this allows us to do is be very flexible. We can have different control objectives. We can formulate constraints, and we can arrive at conditions or notions of global optimality. But of course, we would need extensive communication infrastructure to implement this. Let's see if I can. Oops. Yeah. 1 second. We would also need a system model of the network, and it might be computationally heavy depending on how you implement this. On the other hand, we have decentralized and local information control, as I try to call it, to be as conclusive as possible. So this ranges from simple droop curves, so we're just looking at locally at what's the voltage, and have a proportional way of adjusting either a reactive power output or a real power output of an inverter. That can be a little bit more sophisticated, being an integral control, so trying to have more kind of behaviors that are stable or dampening over time. There are approaches that use sensitivity, so having some notion of how does my local control, my local power consumption or production affect nodes elsewhere in the system. And then there's an interesting paper by one of my colleagues on extremum seeking, which is a way of sending signals into the network at a different frequency with a very small magnitude to kind of use Maxwell, basically the Maxwell's equations, where you get some information back. So you're sending, it's like an echo, you're sending information out. And that, if you do that in the right way, you could actually learn something about what is the gradient value for a specific objective. So you could use that to locally understand, okay, what does the network need based on this lower frequency echo, and adjust your local control accordingly. And surprisingly, that works. It's a really fascinating approach. Anyways, these are some local methods that use local information, or at least have a way of locally determining information in order to do control. And so they need little or no communication. They're often model-free and computationally lighter, but they might, of course, give you, or they will give you suboptimal performance. They tend to rely on a lot of heuristics, and so this is, I think, one of maybe the biggest point to make here is that if we want to do decentralized control, and we end up having to do a lot of tuning and heuristics, we make the lives of utility operators and engineers very hard. So also, most of these methods do not necessarily guarantee constraint satisfaction. And these systems can also easily become unstable if they're not implemented and tuned correctly. So with that, what we try to do is what's the best of both worlds, or how can we combine ideas from both sides in order to do things that take the pluses on this slide with as few possible minuses. So the idea, just to give a high-level introduction of what we did, is that we called it regression-based inverter control at first. We took distribution networks and its model, so we're still model-based in a sense, and historical data of loads and batteries and other generators in the network. And with that, so with this data, we then performed optimal power flow. And with that, you get a data set. So here we see a data set for all the inverters. So let's say I have, in this case, 1, 2, 3, 4, I think 8 or 9 inverters, and x1 up to xn are just all the variables that I have collected for this inverter, including those that came out of the optimal power flow optimization. And so I have these variables, and I also have the optimal control, or the optimal, the minimizer for every, for every time instance. Actually, I said that there were 8 or 9 inverters. These are actually the time, as you can see, small t. These are the different scenarios. So here I have 8 or 9 scenarios. Of course, in reality, I would have a lot more. But X1 might be, the local power consumption for all the inverters. X2 might be the local voltage for all the inverters, etc. So what you then do is if you want to do things locally, you select the local data for one particular inverter, get a smaller data set, including its local or its own optimal set point in green, and you do that for all the inverters. And then what we did next was trying to apply machine learning methods. So here, what we started off with, or what we ended up with, was stepwise regression. In this case, what that means is that we're using these base variables, which in our case were real power demand, reactive power consumption, and inverter reactive power capacity. So we also looked at that the capacity of how much capacity we have might also change over time based on other needs. So if you're, in this case it's reactive power, but you can imagine if you have a battery, you would also have different levels of available real power at particular points in time. So we took those base variables, and with stepwise regression, you are able to use those plus nonlinear combinations, in this case, interaction terms and quadratic terms. And this gives you a regression model that we see here in U hat. And those then become, I've painted them as brains, but those become basically your controllers. So you've learned now a mapping between these local variables and the optimal set points, and then you basically use that as a prediction device, once implemented. And so what this really looks like is like a distributed system where we're using these local base variables that are really the disturbances. So if we go back here, these real power demands, reactive power consumption, they are disturbances, and so they're not necessarily dynamical states in the control theoretic sense. There, for that you would have to assume that your local power consumption does not dynamically vary with voltage, which is is a fair assumption most of the time. So you can treat them as a disturbance variable, and if you look at the classical control theory, you can then use feed-forward controllers that can measure these disturbances and use them to inform a controller. So this is feed-forward, so it's a proactive I see that I'm using this much energy, or I have this much capacity at this moment. This means that the network state might be might be in this state, so I need to provide this much reactive power to the network in order to help the network balance its prevent its contingencies or minimize its losses, etc. That's what we did. And so another flow diagram here is we have a multi-agent system where we've collected this data historically, especially the blue Ds, which are these these base variables that I showed before, and we've augmented that with the red U's. These are the outputs of the optimization scheme of the optimal power flow. And then we split it up into smaller data sets, and that gives us these local policies on the right side, U hat, that are then being implemented in the system. And you could think of this as, eventually, because things change in your network, maybe your data captures like all climates quite well, but maybe at some point there's a new street block that's added, or there's a new there are more and more people like having electric vehicles. So the dynamics that are basically, or the dynamics in the network change, and that's really captured by these mostly by these disturbance variables. So you would have to do this procedure over time. This is a supervised learning method, so it's not a reinforcement learning method, but it's a very efficient one, because once you use this network model, you really an optimal power flow to build these optimal controls, the U's or the U stars. You really you're labeling your data, and you're doing that in a model-based way that really provides a lot of useful structure. And we see that we don't need as much data because of that. And you would compare that with a reinforcement learning scheme. I'd say that's not model-based. I wouldn't know how to do that. So that we were quite excited about this also from a methodological perspective. This is just an example of what the results look like. So on the top, you see all the voltages in a network throughout a day, and on the bottom you see the result of having this decentralized regression-based control, it looks exactly the same as the results from using an optimal power flow scheme. So I'll show you another result later on where it's a little bit easier to contrast the optimal power flow or the centralized result versus the decentralized result. Well, we also saw that because we have this feed-forward control, we're really just adjusting the power outputs throughout the network. And so this is also a relevant feature. Why? Because if you're trying to respond to, let's say, the voltage, which is very dynamically coupled throughout a network, you're doing feedback, of course, in that sense, and you're messing with other kinds of, you're kind of interfering with other devices in a network that might respond to voltage. And so here we're just basically shaping the load profiles, or the nodal power profiles throughout the network. And because of that, we're not interfering with other devices, such as, let's say, a load tap changer, which is a transformer that can dynamically update the voltage most of the time at the top of a network. And here what you see is that even if we implement this scheme, we can then adjust this voltage at the top of the network, and the localized controllers, decentralized controllers, still perform well. They still provide a very narrow voltage band throughout the system. So that is one result. Another one is where we're trying to minimize power. So here we assume that there is a lot of power that can be sourced locally. So we created an objective where we're trying to minimize the power that we source from the substation, from upstream in the network. And so here in blue, you see the scenario of how much kilowatts would be used without control. The magenta dashed line is the amount of capacity. So you see there's a lot of capacity locally in the network. So this might be battery storage, or or like electric vehicles that can share some capacity. And in green, you then see basically the difference between the magenta and the blue line, which is the amount of capacity that you would have to source from the substation. And in red, you then see the result of using decentralized OPF. And so here it's clear that that here there's more of a contrast, but you can still see that like the OPF has a decentralized OPF or data-driven OPF has a pretty good handle on trying to mimic the centralized OPF scheme. Then another result here is for 3 phases. So here the 3 phases are denoted with different symbols. Gray is the scenario before control or without control, and black is with control. And the different numbers on the horizontal axis denote different buses in a network. I think this is actually the 13-node network. It's a smaller IEEE test network that we use. And so you can see that you can even, like the local inverters can learn to adjust their behavior in order to make the voltage across these different phases balanced, or balanced. Just as another result. So what I want to do now is kind of ask a few questions that are more theoretical of like, why does it work and how well? Because in the beginning, we really just tried to use supervised learning. And we saw that it was, quite successful. But under what conditions does it work, and what are some new failure modes? And one of the, the result that these are more questions that I could answer in my PhD, but one of the things that we did was use an information theoretical approach, where again, we're looking at this data set and thinking of it as a compression problem and a reconstruction problem. So basically this step here where we go from like the centralized data set with all the output of the collecting the data and then doing the optimal power flow. We're moving from that big data set to a smaller data set. And of course, we're throwing away some information. And so the question here was like, can we use classical information theory to think of this as a general communication system? And so here we would have the information source would be the centralized source, and the transmitter or the transmitted signal would be the smaller data set, and then the machine learning step would be the kind of the receiver and reconstructor of in terms of the optimal control. So again, we have this decentralized or distributed system, and we can draw a graphical model. So here at the top we see the optimal. So all these variables in this graphical model are now seen as random variables. And at the top we have, for different controllers, C1 up to CC, we have the U stars now being a random variable. So in our case, that's represented by all the values for all the scenarios that we simulated centrally with optimal power flow. So this random variable is really depends on all the states in the network, which is the middle layer of the graphical model. And what we're doing with machine learning is we're really tapping. So yeah, I can show that with this red color. So for this middle control random variable UCI star, it depends on, it will be affected to some extent by all the variables in our network, all the voltages and all the power and the nodal powers. What we're doing is we're really taking only the local variables XCI and trying to reconstruct UCI star as a U hat CI. And so the way to think about this with information theory, for those of you who are maybe less familiar, I was new to it when I started. I started working with a lab mate who had taken a class in information theory, and he said, we should think about rate distortion. And so rate distortion asks the question of, if I want to compress X into R bits, what is the minimum average distortion that I will incur if I try to decompress it again to X hat? And so the answer here is that it's a very general, theoretical idea, but it will give us a numerical tool to eventually to analyze this. And so in rate distortion, you define a metric, and in our case, we really just looked at the square distance, like like the general loss function that you might use in machine learning. And so with that metric D, the minimum average distortion for compression rate R, which I'll come back to what that is given by this expression. So this thing called the minimum average distortion D as a function of R is interesting. It tells you like how good you might be able to do with the data that you have. And it also ends up giving you a sense of, if I don't have enough information, if my distortion is just too high, could I add more features? Could I maybe communicate with another agent, another node in the network? So that's where we're going. And you see that this is subject to the mutual information between X and X star being smaller or equal to R. I think it's easier to see that in the context of our problem, where this can be cast as follows. So we're really looking at the distortion between the reconstructed local U hat and the original U star that was the output of the central optimization scheme. And we see the following constraints. So the mutual information between U hat and U star has to be smaller or equal than the mutual information between the local variables xi and uj. So this holds for all the nodes. Hence we have I and j. But if we just think about like just I, then the mutual information between the two nodes U star and U hat cannot be greater than the mutual information between U star and xi or xci in this case. And so that's maybe intuitive to most of you, but it follows pretty directly from I'm now blanking on one of the key theorems in information theory, but just because you are just because you're using the local variables, like the best you can do is like taking all of the information that those local variables have about the thing you're trying to reconstruct. The second constraint here is that the mutual information between two controllers, so two U hats, cannot be greater than the mutual information of their local variables. And so what that leads to is a theorem, also for restricted communication. So I already alluded to that before. So let's say that your minimum distortion is very high, so you're not able to actually do any good job at reconstructing U star locally. This rate distortion theory gives us a way to understand like what would be the best node to talk to. And this is really interesting, I think, result, because you might think, well, just talk to the node, the closest node next door. But if you think about this in terms of information, you might think, well, isn't the information there very correlated to what I see over here, right? Well, with voltages, we know that's the case. We're also looking at power, maybe the power of my neighbor. Maybe I'm like a supermarket and my neighbor is like a household. It's very different. So maybe that could give me more information about the general state of the network, right? But so we've looked at this, and in the paper that's on arXiv, I give a few. I talk a little bit about what this gives us, but like you sometimes see if you fabricate the experiments in a way where like, oh, there's a lot of correlation in one area, and then a separate area that has its own dynamics or its own information, then you see that the different areas want to talk with one another to improve their local controllers.
By the way, side note, we have 5 minutes.
Okay, yeah, so I'm going to wrap up then. So here you just see what happens if you start adding more nodes. So I've kind of drawn it here, like an extra line between U hat CI and another local variable. So here you just see the mean square error, which is also the thing you're minimizing in a machine learning scheme. But this also tells us like what is the best that we can do by adding one additional etc. K additional observations or nodes that we can talk with. And you can also like compare this for different kinds of models. So here we compare linear models with quadratic models. And we compare the optimal strategy that is based on this rate distortion framework with like a random strategy. So just pick one node and do that, randomize that for all the nodes, just average among all the nodes. So it tells you, shows you that this optimal strategy is successful in a sense. Yeah, so again, this is, we are talking at the moment about can we showcase this on one of the networks, potentially again in the Netherlands, as we have, had good collaboration. So this wraps up these two projects. As I mentioned, the differential privacy would have been a little bit too much, but I'm happy to connect about that later. Yeah, so I think this shows you a journey for me that I've taken where I've spent 5 years in Berkeley thinking about bringing my like control theoretic brain and integrating, like learning a lot about machine learning and seeing how how we can use that to think about automation that is mindful of issues of safety. But also really what's interesting, I think, is that at this intersection of machine learning and control systems, there is a lot of exciting work, especially, well, in my lab in Berkeley, we have work on safe learning. So can you create kind of a safety envelope around the system? So think of a quad rotor having a safety envelope around it that is kind of dynamic based on how certain you are about what's happening, and allows you to learn and to, if you're using reinforcement learning, you might end up getting into a terrain that's unsafe and you might crash. So this safety envelope tries to basically creates a hybrid controller where you're preventing the system from crashing while it is learning. And so, like, just to make the point that I think this intersection of control and machine learning, it's growing, the community is growing, and it's a really exciting place to work. Yeah, I think I'll stop there. I have some more slides here, but I'll just stop here and perhaps address a few more questions.
Yeah, then let's first thank Roel. And so I personally have 2 questions. I see there's also something in the chat. I see it's just a thank you. So if you have questions, you can also turn on your microphone, just ask the question directly, or write in the chat. And if I see it, then I will ask it for you. I guess right now I can start. I have 2 questions, and that is, have you seen applications of this work being implemented in practice?
For the second part of the presentation about decentralized control?
Yes.
So I work with a PhD student in Zurich, ETH. Mm-hmm. And so I've taken the route of like thinking a little bit about different kinds of applications and working with policy, and then he's more taking the route of empirically validating. And so there are certain labs that have test beds where certain people are trying to validate this in the lab. And I think most utility companies are not there yet in terms of having a good infrastructure.
I see. Where
they can do experiments, but maybe I think in a few years this might be very doable. So that's why I'm still in touch with the utilities. I think especially, I don't want to talk for all of the US, but in California, most of the utilities have been investor owned, and they haven't paid much attention to R&D. They've cut a lot of that out, like roughly 20 years ago. And so what we see is that they don't have a lot of like personnel, but also like infrastructure to test these more advanced schemes. And so for that, for me, it made a lot more sense to do that with Dutch utilities, as I'm Dutch myself, and I had actually worked with them before.
Got it. And are you in what sense do you think, are you continuing this type of work, or did you change now in your new environment?
I'm definitely continuing. I'm taking I'm basically adding another area of work, which so far I've been drawing from value sensitive design. And so this is more trying to reimagine or rethink the way we do machine learning, but also just designing systems in general, and trying to do that more in a more participatory way, trying to ask broader questions about fairness, and being more proactive about like what might the emerging issues of solutions like this be. And I think I'm spending more time there now, also because my colleagues here are have those backgrounds.
Yes.
But I do believe that schooling myself in these areas and becoming starting to do more methodological work will also help inform system design.
Yeah.
I think maybe to answer it more compellingly for computer scientists, engineers, is that like control theory used to be like, okay, here's a plane, or here's like a design for a plane or a car. Please engineer, design me a controller that makes it run, efficiently, safely, like no turbulence, etc. Right? And that has already changed, but it's more and more with this like commodity perspective, like control becomes, and like thinking about the dynamics and the impacts and the way things interact becomes part of the design process. And so it's more, thinking more about an integral, I call it integral design approach. I think we need to tap into, HCI, human computer interaction, but also thinking about the social processes and the institutions that might be like in the utility case, you're talking about legacy operating paradigms, but you're also talking about like policy and the politics. So I'm trying to, work on that intersection.
Very nice. Okay. Then does someone else have a question? Otherwise, yeah, thank you again for talking today. And then I'm wishing everyone a nice weekend, and I hope to see you again at the next seminar. Yeah.